All right, let's go over projected coordinates. So these are also referred to as grid coordinates. They represent the projections of geographic coordinates onto a plane through the use of standard parallels and meridians. The positions may be given as x, y, or easting, northing, rather than latitude and longitude. So we have the Cartesian system of x and y, and we can see here there are 4 quadrants, and each zone has an origin, and all coordinates in quadrant 1 will have values that are positive. So here's an example of a UTM, or Universal Transverse Mercator. There may be a false easting or false northing of values to make sure that all values retain positive coordinates. So here we have our false easting and false northing. So we won't see any negative values with the UTM. Okay, so common systems that are used for the states here in the United States, we have the Universal Transverse Mercator, or UTM, and that is projection is based on various datums. So you'll need to check the metadata if you're ever projecting, just to make sure you have the correct datum. And it uses the Transverse Mercator projection. And then we have our state plane systems, and so these will always either be based on NAD 27 or NAD 83. And I guess again, NAD stands for North American Datum of 1927, or North American Datum of 1983, which is the most current one. And the state plane system will be either the Transverse Mercator projection or Lambert Conformal Conic. And again, you just check the metadata to make sure you have the right one. So let's go over the UTM coordinate system. It was developed by the Department of Defense for Global Military Operations. There are 60 zones that cover the globe, and each of them are 6 degrees of longitude. They start at the 180th meridian, and they're numbered west to east. And usually they're measured in meters. So let's take a look at this grid. And so we can see the map of the world has been spread out based on UTM zones. And they range from 1 to 60. And so these are broken into 5, into segments of 5. And so each of these meridians or longitudinal grids are another zone. So it goes 1, 2, 3, 4, 5. A lot of what we'll be working in is zone 10, because we can see here, this is where Humboldt County is. And so a lot of the work that we do for an UTM will be UTM zone 10. Okay, so I'm just going to throw us a couple of examples of UTM zones in different parts of the world, because as we know, in the longitudinal system, the meridians are a lot closer at the poles than they are at the equators, and they get exponentially larger as they reach the equator. And so here in the United States, throughout the whole country, we go from zone 10 all the way to zone 19. And so there's a pretty big group here. They're spread apart. If we were to look at the state of Alaska, which is a lot closer to the poles, we can see that they're just within zones 3 and 7 of the UTM system. And then if we go further down south towards the equator, looking at the state of Hawaii, we can see that they're spread out a lot more, and Hawaii is split up between zones 4 and 5. Okay, so when we have a UTM notation, you're always going to see east and north, right, then up. You have your false easting, northing to keep your positive values, and the notation includes the zone number and the hemisphere. So when we read this sample notation, we're seeing that we have 305,904 meters east of that false easting, And then we have 4,771,651 meters north of the false northing. And we are in zone 16 and in the northern hemisphere. All right, so let's get into state plane coordinate systems. It was developed in the 1930s. It was designed to map the conterminous United States with very little local distortion, measured in feet, and many states have more than one set. So for example, you have Ohio North and Ohio South, which is used for the whole state. And then in California, we have zones 1 through 7. So within the United States, we have 125 zones, and they follow state and county boundaries. And again, the state plane system is based on either the transverse Mercator projection or the Lambert conformal projection. And again, that information can be found in the metadata. And once you start using state plane systems within a state, you just start to know which ones are which. In California, we have the Lambert conformal conic. Okay, so when we see a state plane coordinate system notation, again, always east and north, right, and then up. We have those false easting and northings to keep positive values, just like in UTM. And the notation needs to include the state and zone number. So in this sample notation, we have 2,164,606 feet east of that false easting, and 392,285 feet north of the northing, and we are in Wisconsin. And for Wisconsin, we just have 2, so we have Wisconsin South. Okay, so let's talk about calculating coordinates for the state plane system. And so when we're looking at our USGS topo maps, like I was talking about in the last video, we get a lot of our information down at the bottom of our map. And so here we can see that this is based off of a 10,000 foot grid system based on the California coordinate system, because we are looking at the USGS Arcata South topo map. So we're in Arcata, California, therefore we are in the California state plane system, and we are in zone 1 of that state plane, and it is divided up into 10,000 foot grid system. And so we will be looking at our tick values. So here we know that our state plane system, so we have 1,420,000 feet. Over here we have our UTM, which is 406,000 meters. So those are different, so pay attention. Feet, and then this looks different even. We'll get into this in just a moment, but here we have that denotation of feet, so we know that is our state plane tick mark. Okay, so when we use a roamer, that it can be super helpful to make sure that we're consistent in the distance between our grid lines. And so there are roamers that are divided into meters, and there's roamers that are divided into feet. So you want to make sure that you're choosing the correct one. You can make your own roamer based off of the scale that's at the bottom of the map, and you just want to make sure that when you separate your feet out, that it is the right amount. And so for this roamer here, it says we want to extend the grid line. So we have our grid lines set up, and then we're able to measure from the grid lines using our roamers. And again, like I said, you want to find the right scale roamer, and then we apply it to the grid lines that we're working with. Okay, so because this is set up in meters, we are going to look at our grid lines and our tick marks. So this tick mark here says 4,764,000 meters north, and then from our grid line here, and using our roamer, we can count that this is about 260 meters away from that grid line. And so we're going to add that to our tick mark, which is then going to give us our location of 4,764,260 meters north. Okay, so more coordinates. Let's talk about land partitioning systems. So we have our irregular systems. So we have our English systems. We have meets and bounds, which is an early land partitioning system used in Europe and brought by the English to the original United States colonies. Meets and bounds is an irregular land partitioning system that defines property boundaries using descriptions of geographical or anthropogenic features and landmarks. Sometimes they may contain compass bearings, and they're often from grants or purchases of X amount of acres, and then those acres are self-surveyed. And when we get into the example I'm going to show you, you'll see that it could really lead to a lot of error because certain landmarks might change, especially when they're using trees and boulders and stuff like that. So here's an example of a meets and bounds survey. 5 acres in Hopkinton, Kings County, State of Rhode Island, and Providence Plantation, bounded beginning at a walnut tree, marked on 4 sides, being the northwest corner of said lot, and from thence running eastwardly unto a stake with a heap of stones about it, then southwardly unto the highway, thence by said highway, until it comes to a great oak tree, marked on 4 sides, from thence running northwardly unto the first mentioned bound. So even just reading this out loud for this example, I'm already pretty confused on where they're even talking about. And then they also use different types of irregular units, and these were known units and known standards, but the lingo and everything that is being talked about was definitely hard to follow. So we could see here we have feet and how they're measured, and then units and how much feet that those irregular units are going to be. So we have that normal unit of feet right here. And so a pole is going to be 16 and a half poles, and then change to units is 16 and a half feet, and so forth and so on. And so this led to a lot of irregular lots. And as you can see, rather than a grid line, here in the Virginia Military District, things are just kind of all over the place. So in the US, there are some meets and bounds states. So Texas, or everything here in green, is going to be meets and bounds. And you could usually spot them easily by county lines. So for example, in Kentucky, the county lines are a lot more organic, and that it looks like they were just surveyed by whoever got that lot. And then in Iowa, which uses the rectangular system of survey states or state plane states, and you can see it's a grid and everything is measured out methodically here. So we also have French systems. So we have the cyaneural system, or French long lots. And so they were designed for river access. So a cyaneural system is a system of land distribution established in New France in 1627. This system was designed for river access and dividing the land into seigneuries, long narrow strips frequently called long lots or ribbon farms, each with access to the river in North America. Settlers primarily used these seigneuries in New France as well as parts of the early colonies and territories of the United States. So when I talk about New France, this is parts of Michigan, Wisconsin, Indiana, and Louisiana. Small patches of the Ohio River uses this system, and again, these are also easy to spot by air because they are following the river, as you can see here in those ribbons. There are also Spanish systems, land grants to prior settlers as parts of treaties. They're typically also connected to water.